Welcome back to PathMath 101. You know, inside every modern computer is an absolute marvel of engineering. We're talking about billions of microscopic transistors firing in perfect harmony. But what's truly mind-blowing is that the heart of this futuristic machine is actually governed by a blueprint drawn up all the way back in 1945. Today's explainer is a journey into the von Neumann architecture. We're going to uncover the hidden logic that literally runs every smartphone, laptop, and server on the planet right now.
So you might be wondering, why does a 1945 blueprint cause traffic jams in your brand new cutting-edge hardware? Well, it all goes back to a brilliant mathematician named John von Neumann. He proposed a completely revolutionary idea. Instead of physically rewiring a computer by hand every single time you wanted it to perform a new task, which is how they used to do it, what if we stored the program's instructions inside the computer's memory right alongside the data it was processing? It was pure genius, and it completely birthed modern software as we know it. But as we're going to see, this brilliant stored program concept inherently created a massive physical limitation that hardware engineers are literally still battling to this very day.
To really get this, let's imagine your computer's RAM, the memory, as a giant commercial kitchen pantry. In this 1945 architecture, your data, think of those as our ingredients, which we'll say are packed in blue Tupperware, and your instructions, the recipes telling you exactly what to do with those ingredients, let's say they're in red Tupperware, are packed into the exact same type of containers and stored side by side on the exact same shelf. There is absolutely no physical distinction in the memory grid between a piece of data and a line of code. They share identical memory slots. Now, this unified memory approach makes the system incredibly flexible, sure, but it creates a massive logistical headache when that kitchen actually gets busy.
So, the crucial point here is how the central processing unit, the CPU, think of it as our kitchen's head chef, actually works through that shared pantry. It operates on this endless, looping rhythm, completely devoid of any manual intervention. First, the CPU has to fetch the recipe instruction from the RAM. Second, it must decode that instruction to understand exactly what mathematical operation to perform. And third, it must execute the command, which usually requires it to reach right back into the memory to grab those blue ingredients. Fetch, decode, execute. Millions, sometimes billions of times per second. It's this incredibly fast, synchronized heartbeat.
But here's the catch. This brilliant design creates an absolute nightmare of a bottleneck. Because the recipes and the ingredients live in the exact same pantry, and there's only one physical pathway connecting that pantry to our chef, we get what is famously known as the von Neumann bottleneck. Imagine a single-lane bridge connecting a bustling city to a crucial island. No matter how incredibly fast the CPU operates on the island, and no matter how vast the RAM pantry is over in the city, the ingredients in the recipes must agonizingly take turns crossing that one single-lane bridge. The poor CPU is constantly left starving, just waiting idle for the next packet of data to slowly cross over.
Okay, let's zoom out a bit and see how this builds into the broader system. We know how the CPU talks to the RAM, but take a look around your desk right now. How does the CPU actually talk to foreign, external hardware like your physical keyboard, your mouse, or that high-resolution monitor? I mean, these are entirely alien devices made by completely different manufacturers, yet your processor seamlessly understands every single keystroke and mouse click. How does the architecture bridge the gap to the physical world outside the silicon?
The solution is actually elegantly simple. It's called memory-mapped input/output. Going back to our macro view, think of the computer's motherboard like a sprawling city. To keep logistics simple, the city council decides, hey, we aren't going to build custom, specialized underground tunnels for every single public service. Instead, they just use the existing street grid. They assign a completely standard street address to a residential house, but they also assign a standard street address to the fire station, the hospital, and the keyboard factory. In computer architecture, we don't build custom hardware pipelines for every new USB device. We simply trick the CPU by assigning regular RAM memory addresses to external devices.
To make this whole trick work, standard hexadecimal memory addresses are assigned to literally everything. To the CPU, an address is just a location number. When the CPU reads address 0x00A1, it thinks it's just pulling a normal piece of data from the RAM pantry. But in reality, the hardware has wired that specific address to your physical keyboard. When you press the spacebar, the keyboard places an electrical signal right at that exact address. The CPU has absolutely no idea it's talking to a piece of plastic. It just reads the number at the address, treating external hardware exactly like standard memory. It's brilliant.
So, now that we know how everything is addressed, how does the actual physical data travel across that single-lane bridge we talked about earlier? Well, enter the system bus structure. This is a 3-level logistics superhighway etched right into the silicon, just filled with whizzing binary packets. To make the von Neumann architecture actually function, that bridge is split into 3 distinct lanes. We have the data bus, which acts as our cargo trucks, the address bus, which serves as our GPS system, and the control bus, which manages the traffic lights and the fire alarms.
Let's break down the mechanics of each one, starting with the data bus. Picture these as your bidirectional cargo trucks. They carry the actual heavy payloads, the ingredients and the recipes, back and forth between the CPU, the RAM, and those memory-mapped external devices. And the width of this highway lane is absolutely critical. When you hear people talk about a 32-bit or a 64-bit computer, they are talking about the size of these cargo trucks. A 32-bit truck can only carry 32 ones and zeros at a time. Upgrade to a 64-bit truck, and boom, you instantly double your payload bandwidth per trip, drastically reducing that traffic jam on the bridge.
Next up, we've got the control bus. If the data bus is the trucks, the control bus is the city's infrastructure, regulating all that flow. It acts as the standard traffic lights, sending out routine read or write commands so the RAM knows whether the CPU is taking ingredients out or putting baked goods back in. But, and this is super cool, it also handles something much more dramatic: hardware interrupts. Imagine a quiet classroom full of students focusing on a test. Suddenly, a fire alarm goes off. Instantly, all regular activity pauses. Attention shifts entirely to the emergency, right? Well, when you jiggle your mouse, the mouse sends an interrupt signal down the control bus exactly like that fire alarm, telling the CPU to instantly pause its current math problem and draw the cursor moving on your screen.
Finally, we have the address bus. Now, unlike the cargo trucks which travel back and forth, the address bus is strictly a one-way street. It broadcasts GPS coordinates directly from the CPU out to the rest of the system. The CPU uses this bus to shout out exactly which numbered street address it wants to interact with. It tells the system, hey, I want to read the data specifically located at address 0x00A1. Without this unidirectional GPS broadcast, the cargo trucks on the data bus would have absolutely no idea where to pick up or drop off their payloads. And this right here leads us to a fascinating mathematical limit: 4,294,967,296. Why is this gigantic specific number so crucial? Well, if your computer has a 32-bit address bus, it means the GPS system can only broadcast 32 ones and zeros. Mathematically, 2 to the power of 32 gives you exactly this number of unique addresses. Since each address holds exactly 1 byte of data, a 32-bit GPS system can only physically find a maximum of 4 gigabytes of RAM. This is the exact reason why old 32-bit computers fundamentally could not use more than 4 gigs of memory, no matter how much you physically plugged into the motherboard. Bringing it all together, all these hardware gears just lock perfectly into place. John von Neumann's 1945 blueprint, storing data and instructions in one shared memory, created the software revolution. We use memory-mapped I/O to cleverly trick the system into talking to keyboards and monitors. And we use the incredibly precise logistics of the data, address, and control buses to manage the heavy traffic flowing across that single-lane bridge. It is an utterly unified, perfectly synced clockwork machine operating billions of times per second right under your fingertips.
And that, my friends, is the theoretical beauty and the fundamental limitation behind the von Neumann architecture. If you want to master these fundamentals and continue exploring these incredible systems, make sure you subscribe to PathMath 101. But I want to leave you with one final thought for today's explainer. As our demand for exponential processing power absolutely skyrockets with things like AI, will we ever break free and invent a completely new blueprint, or are we forever trapped in a traffic jam designed all the way back in 1945?